All right, well, welcome to our lecture recording for section 5.6. We've got one more section to cap off chapter 5. So remember, chapter 5 is our introduction to sequences and series. We're learning the theory of these things so that in chapter 6 we can begin applying them to the problem of creating power series to approximate transcendental functions. Okay, I don't know why this looks whopper-jawed to me. It doesn't matter. We're not going to be looking at me very long anyway. Um, we've gone through a series of sections where we've been learning different convergence tests for infinite series. We have one more major test that we need to learn, and this is probably the one that we're going to use the most in chapter 6. So we'll do several examples and try to cover this pretty thoroughly. There's also there's a second test we'll learn in this section. We'll just do a couple examples of that. It won't come up quite as much. And then that'll pretty much take care of what we need to know about testing convergence, and we'll be ready for chapter 6. All right, let's have a look at section 5.6. All right, now so far, we've not really tried to determine the convergence of many series that contain factorials. I think we did like one example along those lines. The reason for that is the convergence tests that we've used so far, things like the limit comparison test, and the integral test, and the p-series tests, and the geometric series tests, and the alternating series tests, those things don't work particularly well for problems with factorials. I think we did one very specific example where we were able to make a limit comparison test work. But generally, none of those are really the ideal test when you're working with factorials. However, in chapter 6, we will begin building infinite series from scratch, and the process we're going to use for building them is going to generate factorials. So we're usually going to see those in our answers after when we're constructing a series. Okay, so knowing all that, it might seem suddenly important to have a test that works well for series that have factorials in them. And in fact, there is such a test. And in a lot of ways, it's a little nicer and easier to use than some of the tests we've looked at already. Okay, now, it's not a be-all and end-all. There are some series that it doesn't work well for, which is why we need those other tests, but it does work nicely for series with factorials, which is a lot of them. So, key idea for this section, theorem on page 509, the ratio test. Okay, so here's our ratio test. Okay, so it says, let's assume we're looking at a series with non-zero terms. Okay, the reason why we can't have zero terms in the series is because we're going to be dividing by the terms down here. Okay, but you know what, that's pretty much it in terms of restrictions. Okay, a lot of our other tests, the terms had to be positive, or it had to be an alternating series. But this test can really kind of handle any of that as long as we don't have zero terms to screw it up. And generally, if there would be zero terms, we just rewrite the series without them. So here's what we're going to do. We're going to compute a limit. Okay, and it'll be a limit of a ratio of basically a term to the term before it. Okay, a sub n plus 1 over a sub n. Okay, we're going to compute that limit if that limit is anything less than 1. Now notice we put the ratio in absolute values, so we don't have to worry about it coming out to be negative. It'll be at least 0. Okay, but if it's between 0 and 1, not including 1, then the ratio test that says that our series converges, not just converges, it converges absolutely. Now remember, converging absolutely means that it converges, but it's actually a little stronger statement. Okay, it means it would converge even if we dropped out any negative signs on the terms. Okay, but it definitely converges. Now on the other hand, if that limit turns out to be something greater than 1, or if it turns out to be infinity, then the test says that the series diverges. Now, it is possible that that limit would turn out to be exactly 1, and in that case, we say that the test does not provide any information, And the reason we say that is because in that scenario, the series could be convergent or it could be divergent, and we'll have to use a different test to get at the answer. Okay, so this is kind of like the one big weakness of the ratio test. The idea behind the ratio test is we're basically testing to see if the series is behaving like a geometric series. With a geometric series, we always multiply one term by the same constant to get to the next term. That's what we call r. If the constant you're multiplying by is something less than 1, like 1/2, then that geometric series is going to be convergent. If it's something bigger than 1, like 2, then that geometric series is going to be divergent. But in a geometric series, that 1/2 would be the ratio of a sub n plus 1 over a sub n. It would be the ratio of any term to the previous term. Okay, so in particular, if we applied the ratio test to a geometric series with an r value of 1/2, then we would get, I should say what this letter is here. This letter that they're using that looks like a P, it's the Greek letter rho. We've encountered that before when we talked about densities. So the book is using rho to refer to the limit. Alright, so if we applied this test to a geometric series with an r value of 1/2, then our limit would be rho equals 1/2, and according to the test, we would conclude that the series converges, which we know is right for a geometric series with an r value of 1/2. What this test is saying is that if the limit of your ratios is 1/2, then your series is basically like a geometric series whose common ratio is 1/2. And on the other hand, if the limit of the ratios of your terms is something bigger than 1, well, then your terms are clearly growing. Okay, and this is like a geometric series with a common ratio bigger than 1. Okay, if that limit turns out to be greater than 1, then we know the series diverges. And in fact, while we're not going to go through the proof of the ratio test, the proof actually uses geometric series. Okay, so you could almost call this the geometric series test, because we're testing the series to see if it behaves like a geometric series. Alright, let's look at an example from the book. We'll start with number 317 from the book. Let's roll down and see what the instructions have to say about that. I don't know why, but I sing nonsense to myself whenever I'm scrolling. Aha, here we go. So, use the ratio test to determine whether the series, whose nth term is a sub n, converges, where a sub n is given in the following problems. Okay, state if the ratio test is inconclusive. So, in 317, the nth term of our series is 1 over n factorial. Okay, so this is exactly the sort of thing that I said the ratio test would be good for. Alright, so let's have a look at this problem here. To apply the ratio test, we would take the limit as n goes to infinity. Now remember, we put the ratio in an absolute value, and then we start with the n plus 1 term. So if this is the n term up here, the n plus 1 term would be 1 over n plus 1 factorial, and then we divide by the n term, so 1 over n factorial. Now for this particular series, everything is positive, so I'm going to drop off these absolute values. They're not really changing anything, but I wrote them there just as a reminder. Sometimes we do need them. Alright, so we're taking the limit as n goes to infinity of 1 over n plus 1 factorial times, now since I'm dividing a fraction, I'm going to flip that fraction. I'm going to make that n factorial over 1. Okay, now with factorials, it helps to expand them out. So we'll take the limit as n goes to infinity of, alright, so n factorial is the only thing really in our numerator. N factorial is n times n minus 1 times n minus 2, and we just keep decreasing by 1 all the way back to 3, 2, 1, however far we have to go. N plus 1 factorial would start with n plus 1, and then we decrease by 1 to get n, and then n minus 1, and then n minus 2, and all the way back to 3, 2, 1. Now notice, everything is going to cancel. All these factors cancel, except that n plus 1 in the denominator. So now we have the limit as n goes to infinity of 1 over n plus 1. Okay, and of course, that's easy to compute. That goes to 0. Okay, but since 0 is less than 1, we'll go ahead and write up our conclusion here, just like we would when we're applying any convergence test. Since 0 is less than 1, the ratio test allows us to conclude that this series we were talking about, the series where n goes from 1 to infinity and the nth term is 1 over n factorial, okay, allows us to conclude that this series is convergent. In fact, absolutely convergent. But it wouldn't be wrong if we wrote convergent. Since this series has all positive terms, alright, got disrupted there, but I'll finish writing this. Alright, and we're able to conclude that this series is absolutely convergent. Alright, let's look at some more examples. Alright, so here's another example. This one is based on problem 319 from the book. Same directions, use the ratio test. Now I did add a little something. 319 just had n squared over 2 sub n as the nth term. I added in this negative 1 to the n plus 1 because I wanted to make this one like an example we did in the previous section where we used the alternating series test. Okay, with that factor of negative 1 to the n plus 1 in there, this series is an alternating series, and therefore we were able to use the alternating series test, but the alternating series test was a little bit tricky, and it was mostly tricky because of this 2 to the n. Okay, that 2 to the n, I mean, it didn't stop us, but yeah, it made it a little bit harder to apply L'Hopital's rule because we had to review how to take the derivative of an exponential function. And it also made it a little bit trickier to show that the absolute values of the terms were decreasing. Yeah, we actually had to do a little bit of Calc 1 stuff there to make that happen. I wanted to come back and do this same problem, but using the ratio test. It actually turns out to be quite a bit easier using the ratio test. Okay, let's have a look at this. So with the ratio test, we take the limit as n goes to infinity of the absolute value of the n plus 1 term. So for the n plus 1 term, we have to go everywhere that we see an n, okay, and put a plus 1 with it. So negative 1 to the n plus 1 times n plus 1 squared over 2 to the n plus 1. Alright, all of that is our n plus 1 term. And then we divide by the n term. Okay, now we know that whenever you divide by a fraction, you're going to flip it and multiply. So let's just go ahead and flip this. The 2 to the n will go in the numerator, and the negative 1 to the n plus 1 will go to the denominator, and the n squared will also go to the denominator. Okay. Now, one thing I want you to see is that when we apply the ratio test, because we're taking an absolute value of the ratio, any factor whose only effect is to make things negative or not negative is basically going to be squashed by the absolute value. This factor is always 1 or negative 1. Well, the absolute value of either of those things is 1. So basically we can drop this out and drop this out because they're both turned into 1s by the absolute value. So let's go ahead and rewrite this. Once I drop those things out, I no longer really need the absolute value because everything else is already positive. So we'll have a limit as n goes to infinity. Now that n plus 1 squared, I could go ahead and expand that out as n squared plus 2n plus 1 over 2 to the n plus 1 times 2 to the n over n squared. Okay, now I'm going to do a little rearranging here. Basically, I'm just going to swap the denominators. So I'm going to rewrite this as n squared plus 2n plus 1 over n squared times 2 to the n over 2 to the n plus 1. Now here's what that does for me. This first fraction is now a rational function, and the top and bottom have the same degree. So when n goes to infinity, this fraction just becomes the ratio of those leading coefficients. In other words, it becomes 1. Okay. Well, alright, so we know what that becomes. Now, let's look at this second fraction. We can actually simplify this quite a bit because we have like bases. With like bases, we can use a rule that says, this is just a rule for exponents, like something you learn in high school algebra. A rule that says you can subtract the powers. N plus 1 minus n is 1. So what I'm left with is a 2 to the 1 down here and just a 1 up there where the smaller power was. Okay, so now I have a limit as n goes to infinity of a fraction that I already know is going to go to 1 times a fraction that could be simplified to just a half. So that limit is going to be 1 times a half, which is a half. Okay. Now remember, if the limit in a ratio test turns out to be anything less than 1, we can conclude that our original series was absolutely convergent. So, by the ratio test, and let's go ahead and capitalize ratio there. By the ratio test, our series, where n goes from 1 to infinity, and the nth term is negative 1 to the n plus 1 times n squared over 2 to the n, is absolutely convergent. And so it's convergent. I would actually say that that was quite a bit easier to do than using the alternating series test, because with the alternating series test there's 3 conditions. One is always easy, just that it's an alternating series, but then there were 2 other conditions that had to be tested, that it was decreasing and that its limit was 0. Okay. Here we really just had one condition to test, the condition that the limit of the ratio of a term to its previous term would go to something less than 1. Okay. I've told you already that if a series has a factorial in it, then you should probably use the ratio test. But also the ratio test works well when there are exponential terms. So we'll say this, the ratio test also works well for series with exponential terms. Let's try again to spell exponential. Exponential. Haha. I mean, here's the thing. When you've got exponential terms, or in this case, maybe it would be better to say exponential factors. Yeah, let's say factors since it's part of a larger product. Exponential factors. Okay. The term is all of it. Okay. When you've got those exponential factors, those pieces of the term are basically like a geometric series. I mean, if the only thing here was 1 over 2 to the n, that would be a geometric series with an r value of 1/2. Okay, and we would definitely expect that to be convergent. Okay, but since there's also something that might be making it divergent, okay, having an n squared in the numerator has a tendency to push the fraction towards infinity, even while having 2 to the n in the denominator is pushing it towards 0. You know, it's a little unclear what's going to win out. Who's growing faster? Is this thing going to infinity faster, or is this thing? Generally speaking, exponentials outweigh polynomials. And it's also usually the case that factorials will outgrow exponentials. So there's kind of a hierarchy. I would kind of expect this exponential to win out over this polynomial. The ratio test gives me a good way for testing that. Okay, so my recommendation is apply the ratio test anytime you see either exponential factors or factorial factors within your terms. Okay, that would probably be the go-to thing in those scenarios. Now, there is a case where the ratio test doesn't work particularly well at all. Okay, let's look at an example like that. Let's do this one. This was part of my list on page 1 of the outline. Okay, here's a series where the nth term is 3n plus 5 over n squared. Okay. So for this one, notice the top is a polynomial, the bottom is a polynomial. There's no exponentials, there's no factorials. Okay. Now, you can probably see at a glance that the top has degree 1, the bottom has degree 2. The difference of degree is 1. So this is probably like a p-series with p equals 1. Okay. So this is like 1 over n to the p, where p equals 1, which is divergent. Okay, so I would expect this to come out to be divergent. Okay, and in fact, if I do a limit comparison test, let's do that first. This is what we learned how to do in section 3.4. Limit comparison test. Then, so for a limit comparison test, I would want to take the limit of the ratio of the nth term of the series I'm testing to the nth term of the series that I believe it's like. So I take the limit as n goes to infinity of 3n plus 5 over n squared divided by 1 over n. So let me see. That would be the limit as n goes to infinity 3n plus 5 over n squared times n. But then I can do a little canceling and say, alright, well that's the limit as n goes to infinity of 3n plus 5 over n. Now, since the degrees match, I can say, well, that's just 3. Now remember, for the limit comparison test, all that mattered was that the limit was a finite number other than 0. So since this limit is a finite value, it's not infinity, and it's not 0, okay, and it's not 0, the limit comparison test allows us to say that both of these two series would have the same convergence or divergence, and we know that one is a divergent p-series. So since this limit is a finite value, and it's not 0, and this series, where the nth term is 1 over n, is a divergent p-series, okay, so since we got all of that going for us, we can conclude that this series we're testing, the series where the nth term is 3n plus 5 over n squared, is divergent by the limit comparison test. Now, let's see what happens with the ratio test. Ratio test. So for the ratio test, rather than taking the ratio of our nth term to the nth term of some other series that we're going to compare to, we're going to take the ratio of our n plus 1 term to our nth term. So one nice thing about the ratio test is you don't have to come up with another series to compare to. Okay, you're just comparing it to itself, basically. Okay, so this would be the limit of the absolute value. Now for the n plus 1 term, we've got to slip in a plus 1 on all of our n's. Okay, and then we're going to multiply by the reciprocal of the n term. So remember, the n term was 3n plus 5 over n squared, but we're dividing by that, so we're going to multiply by its reciprocal. Alright, now I don't really need that absolute value since everything is positive. So I'll go ahead and drop that out. Okay, so I've got a limit as n goes to infinity of, 3n plus 3 and plus 5 makes plus 8. Now, I'm going to go ahead and, since this has the same degree, I'm going to tuck it under there. And I'm going to put this under the n squared. N plus 1 squared is n squared plus 2n plus 1. But here's the thing. Both of these fractions, since the degree of the top matches the bottom on both of them, they're both, this one goes to 3 over 3, this one goes to 1 over 1, so this goes to 3 over 3 times 1 over 1, which is of course 1. Okay, now remember, the ratio test, let's look at it again. Scroll back up here to page 509, I think it was on. Oops, that's the root test. We'll talk about that later. Using the ratio test, we're almost there. The ratio test told us that if the limit is less than 1, then we can conclude that we have absolute convergence. And if the limit is greater than 1 or infinity, we can conclude divergence. And we know that in this case, that should be the correct conclusion. But the ratio test tells us that if the limit is 1, then it doesn't provide any information. Now at the moment that seems a little odd, because it feels like, hey, we know the answer is divergent, why can't we conclude divergent? Okay, But I'm going to show you another example to kind of clarify why it is that the theorem says that if the limit is 1, we shouldn't draw any conclusions from the ratio test. Alright, so let's look at another example. Okay, now notice this one was like a p-series where p would be 1. This is another example from my outline though. This one, sum where n goes from 1 to infinity, and the nth term is 5 over n squared. This is a p-series with p equals 2. This is a p-series with p equals 2. Okay, remember we said that having a constant multiplier doesn't really change anything when we're examining convergence or divergence, as long as the constant isn't 0. This is a p-series with p equals 2, so it is convergent. Okay, we don't even have to do a limit comparison test to sort this one out. We know the answer. But let's see what happens when we apply the ratio test. When I apply the ratio test, I'm taking a limit as n goes to infinity, absolute value. My n plus 1 term is going to be 5 over n plus 1 squared. And then I need to multiply by the reciprocal of the n term. Alright, well I guess I can cancel out those 5's and say, alright, well that's the limit as n goes to infinity. And I'm not going to need the absolute values, everything's positive. That's just going to be n squared over n squared plus 2n plus 1. And that limit's just 1. Okay, so here's the deal. Sometimes when the limit of the absolute value of a sub n plus 1 over a sub n equals 1, the series is convergent. Okay, but other times it's divergent. And that's the reason that we say we can't draw any conclusions when that limit is 1. So we never try to draw conclusions from the ratio test when this limit is 1. Okay, but let me tell you what the real problem is. The real problem is we were applying the ratio test to series where the nth term was a rational function. That was the problem here. That was the problem here. Notice that in the numerator and the denominator we had polynomials both times. No exponentials, no factorials. Okay? You see exponentials or factorials, that should be your clue to use the ratio test. But if you're just seeing polynomials, one, you could probably use a simpler test like the limit comparison test, and two, the ratio test probably isn't going to help you. Okay, so that's something to think about. Alright, let's do some more examples where we can draw some conclusions from the ratio test. Alright, so here's another problem straight out of the book, problem 321. The instructions again are to use the ratio test to try to draw a conclusion about whether this series converges or diverges. Now, right off the bat, you can see factorials in it. That's a strong hint that we should use the ratio test. The ratio test usually works well when there are factorials present, and typically other tests are going to get messy. So definitely a strong indicator we should use the ratio test. So we're going to take the limit as n goes to infinity. Okay. Now we start with the n plus 1 term. So for the n plus 1 term, we add a 1 directly onto the n before anything else applies, even like a factorial. So that n factorial becomes n plus 1 factorial, and then that whole thing gets cubed over 3 n plus 1 factorial. And then we're going to multiply by the reciprocal of just the n term. So we'll flip this fraction over. We'll put the 3n factorial on the top over the n factorial cubed. Alright, now since everything is positive, I can go ahead and drop these out, but I always put them there in the beginning just so that I don't forget that we're really taking the limit of an absolute value. Okay, sometimes that matters. Okay, we'll see more examples like that later. Alright, so n plus 1 factorial. Let me see, n plus 1 factorial would be n plus 1 times n minus 1, and then all the way back to 3 and 2 and 1. But then that whole thing is cubed. So basically that means all of those factors are cubed, because we know that cubes can distribute over multiplication. Now down here, now here's something that I should probably clarify because it hasn't really come up yet. But we've got multiplication and we've got a factorial. Okay? Factorials are considered to be higher priority in the order of operations than multiplication. So it's n plus 1 factorial times 3. Okay? So really I just have a 3, and then I have the n plus 1 times n minus 1 all the way back to 3, 2, and 1. Okay, there's my first fraction. Second fraction. So again, factorial comes before multiplication, so I just have a 3 and then the n factorial. N times n minus 1 all the way back to 3, 2, 1. And down here I've got that same thing again, n times n minus 1 back to 3, 2, 1, but it's cubed. Oh, and I said I wouldn't write the absolute value anymore, so let's fix that. Alright, well, it looks like there's a lot of opportunities for canceling. Let me go ahead and catch the low-hanging fruit. 3, boom. That was easy. Now check this out. All of these factors are cubed. Down here they show up not cubed. So I can cancel one factor of n plus 1, and up here the power of n plus 1 would drop from 3 to 2, and the same for all of these others. One factor of n, the power of n would drop from 3 to 2. I can just do that all the way across. So basically I'm left with, instead of n plus 1 factorial cubed, I'm left with n plus 1 factorial squared. Okay. Very similar thing I can do over here. In the bottom everything is cubed. In the top everything shows up once. So I can cross out everything in the top and then change the power in the bottom to a 2. Okay. So let's see what we have left. We have a limit as n goes to infinity of, let's go ahead and distribute this power. I've got an n plus 1 squared, and an n squared, and an n minus 1 squared, and a 3 squared, and a 2 squared, and a 1 squared. And in the denominator I have all of this stuff left. So an n squared, and an n minus 1 squared, all the way back to a 3 squared, and a 2 squared, and a 1 squared. And you know what? Look, I get all kinds of cancellations. Boom, boom. There's the only thing left. So I'm left with a limit as n goes to infinity of n plus 1 squared. Well, in this case, since that's not in the denominator, as n goes to infinity, that thing's just going to infinity. So my limit is infinity. Now, according to my ratio test, okay, if my limit, so remember the ratio test was calling the limit rho, if my limit is greater than 1 or it's infinity, then we conclude that the series diverges. Okay, alright, so shut that back off. So since that came out to be infinity, we can say by the ratio test, our series where n goes from 1 to infinity, and our nth term is n factorial cubed over 3 n factorial. You know what? I guess it's not a big surprise that this diverges. I might have guessed that at the front end just because we had factorials top and bottom, but on top of having a factorial, we also had that factorial was cubed. So I would kind of expect that the top of the fraction would outgrow the bottom of the fraction, and that's going to make this thing diverge. Alright, let's do one more problem out of the book, and then I've got an example that's kind of a forward-looking example to show us how we'll be using the ratio test in the next chapter a little bit. And then a couple of quick examples on the root test. So we're coming along well. Alright, this is problem 324 from the book. The instructions are still the same. Use the ratio test and, if possible, conclude that the series is convergent or divergent. Okay. Now, let's just kind of look at what we've got. I've got a factorial in the numerator. Okay, now notice, again, there's multiplication and a factorial, but this time the parentheses are telling us that the multiplication is first and then the factorial. So this isn't 2 times n factorial. This is the factorial of 2n. So it'll be 2n times 1 less than 2n times 2 less than 2n, and so on. Now on the bottom, I've got kind of a double whammy here. Having n in the power makes it exponential. Having n in the root makes it polynomial. So it's not really either of those things, it's kind of a combo of the things. Now I would expect a factorial to outgrow either of those. Okay, but I don't really know. Will it outgrow something that's kind of both? Well, maybe the ratio test will help us sort that out. Okay, it's kind of hard to have an intuition going into this one. We'll just have to see how this shakes out. Alright, so let's take the limit as n goes to infinity of the absolute value of our n plus 1 term. So when I stick this plus 1 on the n, it has to affect the n before anything else, even the 2. So 2 times n plus 1, and then all of that is factorialed. And yes, I just made up a verb, but you know what I meant. Okay, same deal down here. It's 2 times n plus 1, and then all of that is raised to n plus 1. And then we multiply by the reciprocal of just the n term. So 2n to the n over 2n factorial. Boom. Alright, I think we're going to have to do just a little bit of simplifying there. On the top, I'm going to go ahead and multiply this out and say this is 2n plus 2 when I do the multiplication. That's what I'll be taking a factorial of. Now on the bottom, I don't really need to keep the absolute value since there's no negatives. On the bottom, I have a product raised to a power. I'm going to use the rule that says that powers can distribute over products, just because I can kind of see that if I do the same thing up here, I'll be able to get a 2 to the n to cancel out. Okay, and that'll be kind of handy. I mean, at least get something to go away. Alright, so down here, distributing my power, I get 2 to the n plus 1 times n plus 1 to the n plus 1. Okay. Times, alright, I'll do the same thing here. I'll distribute the power over the product. 2 to the n times n to the n. And then I've got a 2n factorial. Alright, let's keep working. This one's a little bit longer, but one of the things I want to make clear to you guys is that if you take your time and you're careful with the algebra, I mean, there's some little places where you can get tripped up, but if you take your time, hopefully you'll eventually get it to knock down enough that you'll be able to see what the limit is. Alright, so limit as n goes to infinity. Now 2n plus 2 factorial would be 2n plus 2 times 1 less than 2n plus 2 would be 2n plus 1, and then 1 less than that is 2n, and then 2n minus 1, and then so on down to 3, 2, and 1. Okay, now I'm going to go ahead and put this underneath that. 2n factorial would be 2n times 1 less than 2n, and then all the way back down to 3 and 2 and 1. Okay, so that's taking care of this numerator and this denominator. Okay, now I still have the other numerator and denominator, but I can knock that down a little bit too. Okay, if I focus on 2 to the n plus 1 and 2 to the n, those have exactly the same base. So I can subtract the powers. N plus 1 minus n is, well, it's just 1. So I'm left with one factor of 2 down here. So I'll keep that. And I've still got this n plus 1 to the n plus 1 and an n to the n. Alright. Now, I can do some canceling over here with the factorials. Basically, with the factorials, everything's going to cancel out of there except the 2n plus 2 and the 2n plus 1. Alright, so let's write a cleaned up version of this. This is the limit as n goes to infinity. So what do we got left here? We've got a 2n plus 2, a 2n plus 1. Now, times an n to the n over a 2, okay, a 2 times an n plus 1 to the n plus 1. Now I'd like to do some simplifying here, but the problem is I don't have either the base matching or the power matching. Okay, I have some rules for exponents that I can use. Okay, kind of an aside here. Aside. Rules for exponents. So one rule says that if the bases match and I have different powers, so like say I have a to the b over a to the c, okay, if I got that kind of thing going on, if the bases match, then I can just subtract the powers. Okay, I've got another rule that says if the powers match but the bases are different, then I can rewrite that as one fraction raised to that common power. Right now, since I don't have matching bases and I don't have matching powers, I can't really use either of those rules. But here's one thing I can do. Okay, n plus 1 to the n plus 1 means basically I've got this factor, n plus 1, this many times. Okay, so I've got n plus 1 factors of n plus 1. Let's pull one of them out. So I'm going to rewrite this as a limit as n goes to infinity of 2n plus 2 times 2n plus 1 times n to the n over 2, and I'm going to pull out one factor of n plus 1, and that just leaves me with n plus 1 to the n. It also lets me do a little canceling, because 2 times n plus 1 is the same thing as 2n plus 2. That's kind of nice. Alright, so now I've got a limit as n goes to infinity. I've still got this factor of 2n plus 1, but over here with these guys, because I've got a matching power, now I can use this rule and say, alright, that would be equal to n over n plus 1 to the n. Alright, now it may not immediately be obvious where I'm going with this, okay, but there is actually something I can make use of, and it's something we talked about and then we haven't really talked about it since, so I thought this would be a nice chance to review it. This is almost the fraction raised to a power that becomes e when you send it to infinity. Okay, I say it's almost because the thing that would go to e would be n plus 1 over n rather than n over n plus 1. So it's the reciprocal of something we know what to do with. So what I'm going to do is I'm going to move this factor to the denominator so that I can flip it over. So I'm going to say this is the limit as n goes to infinity of 2n plus 1 divided by the reciprocal of this thing, n plus 1 over n to the n. Okay. Now, I will just mention, it might be a little clearer if I rewrote this. N plus 1 over n is the same thing as 1 plus 1 over n to the n. Okay, that goes to e. But our numerator goes to infinity. If we're taking a limit, the numerator is going to infinity and the denominator is going to a constant, the value of the limit is infinity. Aha! So the ratio test is conclusive. The ratio test tells us conclusively that this series is divergent. So, by the ratio test, our series, our n goes from 1 to infinity, and remember we had 2n to the factorial over 2n to the n, is divergent. And if it's divergent, that means that the top is either it's outgrowing the bottom or at least it's keeping pace with the bottom. Okay? If this fraction is going to anything other than 0, then the series would be divergent. That's our divergence test. Okay? So the top is at least keeping pace with the bottom. Okay, so apparently a factorial can at least keep up with a polynomial mixed with an exponential. Okay, and I'm guessing it probably actually outgrows it. Okay, interesting. Yeah, actually, we can definitely say it outgrows it because this wasn't a number bigger than 1. This was infinity. Okay, so the ratio of each term to the next term is growing without bound. So the terms are going to infinity. So anyway, interesting result there. Alright, now here we are at the bottom of the first page of our outline. I wanted to do one more ratio test problem, one that kind of foreshadows what we're going to be using the ratio test for in chapter 6. Okay, now here is an infinite series where we've written out the first 5 terms. Okay, that should be enough for us to kind of pick up the pattern. First term is pi over 2, and then minus pi over 2 cubed over 3 factorial, and then plus pi over 2 to the 5th over 5 factorial, and then so on. Okay, we're going to show that this is a convergent series. Now the fact that I'm seeing factorials is immediately making me think, we're probably going to need to use the ratio test here. Okay, But to use the ratio test, I need a formula for the nth term. I need to know what a sub n is. Well, there's a couple things to think through here. One, I see that this is an alternating series, so I'm going to need a -1 raised to a power. And it looks like we're going to start out positive and then go negative. So we'll want that power to be n plus 1. If we were starting negative and then going positive, the power could just be n. Looks like I need pi over 2, since that's there in all of them. But you know what? That pi over 2 is raised to a power. I guess we could think of this as 1, and then 3, and then 5, and then 7, and then 9. So the powers are odd numbers. Now to get even numbered powers, we would do 2n. Okay, 2n will always be even, no matter whether n is even or odd. Okay, I want it to always be odd. So to get odd numbers, you could do 2n plus 1, or you could do 2n minus 1. Now in this case, since the power starts at 1, and presumably n is going to start at 1, I'm going to do 2n minus 1, so that when n is 1, 2n minus 1 would be 1. When n is 2, 2n minus 1 would be 3. When n is 3, 2n minus 1 would be 5, and so on. And then I need the factorials down here to track with the powers. 3 factorial, 5 factorial, 7 factorial. Now in the first one, there's no factorial written, okay? But 1 factorial is defined to be 1. So if I had put a 1 factorial in the denominator, it wouldn't change anything. So I need a denominator that is a factorial that matches that power. Okay, now I'm in a position to use the ratio test. I know what the nth term looks like. Okay, I have a formula for it. So now, referring back to my nth term there, let's see if I can slide that under there. I can say, alright, we are going to take the limit as n goes to infinity of the absolute value. Now we're actually going to start with the n plus 1 term, so I've got to add a plus 1 to all of these n's. So -1 to the n plus 1 plus 1, okay, times pi over 2 to the 2n plus 1 and then minus 1 all over 2n plus 1 minus 1 factorial. Alright, that's my n plus 1 term. And then we need to divide by the n term, which is this. And to divide by a fraction, we'll multiply by its reciprocal. So we'll put that -1 to the n plus 1, and the pi over 2 to the 2n minus 1, we'll put all that in the denominator, and the 2n minus 1 factorial, we'll put that in the numerator. Alright, now here's one nice thing. Okay, because we're taking an absolute value, these two factors here can just be gotten rid of, because all they do is multiply by 1 or -1, and that is completely squashed by the absolute value. Okay, so the ratio test is kind of a nice thing to apply to alternating series, because we don't have to worry about those negatives. Okay, now that I've gotten rid of those, I don't really need the absolute values anymore. Everything else is going to be positive for us. So what have I got here? I've got pi over 2, and the power is 2n plus 2, but then minus 1. 2n plus 2 minus 1, that's 2n plus 1. So I guess down here I'm also going to have 2n plus 1 factorial, and then 2n minus 1 factorial, over pi over 2 to the 2n minus 1. Alright, well, the low-hanging fruit here is these exponential factors. I've got the same base, so I can just subtract the powers. So 2n plus 1 minus 2n minus 1. Well, 2n plus 1 minus 2n minus 1 is 2. Okay, 2n plus 1 is 1 higher than 2n, and it's 2 higher than 2n minus 1. So I can cross these out and say I'm just left with a pi over 2 to the 2. Now for the factorials, 2n plus 1 factorial would be 2n plus 1 times 2n, because that's the number that's 1 less than 2n plus 1, times 2n minus 1, and then from this point backwards, 2n minus 2, 3 times 2 times 1. From this point backwards, this is just 2n minus 1 factorial. So I can cross this against that, and I can say, alright, this is the limit as n goes to infinity of pi over 2 squared, which is a constant, over 2n plus 1 times 2n. Now here the bottom's going to infinity and the top is held constant, so that limit is 0. Okay, and if the limit is 0, when we're taking the limit of the ratio of the n plus 1 term over the n term, then we can use the ratio test to conclude convergence. So, by the ratio test, this series converges. Alright, now that was part A, prove that the series converges. Presumably there must be another part here. Let's see what part B says. Part B, determine how many terms would be needed to approximate the entire infinite sum accurately to 3 decimal places, and then compute the corresponding partial sum. Well, see, here's the thing. This was an alternating series, so the error when we do a partial sum with, let's say we did a partial sum with 5 terms, the error would be less than the 6th term. Okay, if I did it with the first 5 terms, n equals 1 through 5, then I could just compute the term where n is 6, and that would be my error. But here we're being asked to figure out how many terms would be needed to make sure that our error is small enough that we would be accurate to 3 decimal places. So let's do a little interpreting here. Part B. So accurate to 3 decimal places. Okay, this is what we were asked to do. That means that the error is less than, so if I want 3 decimal places, I'm going to do a decimal and then 3 zeros and then a 5. Okay, being accurate to 3 decimal places means that if we round our approximation to 3 decimal places, it'll match the true answer to 3 decimal places, and that'll happen as long as we're off by less than half of a 1 in the 3rd decimal place. Okay, so we need our error to be less than that, but then since this is an alternating series, since this is an alternating series, if I were to take the difference between, let's let S be the sum of the whole series, and S sub n be the partial sum of the first n terms, okay, that difference has to be less than the absolute value of the n plus 1 term. Okay, this is our error. The difference between the sum of the whole series and the partial sum. Okay, so if we make this thing here, the absolute value of the n plus 1 term, less than 0.0005, we'll be forcing the error to be less than 0.0005. Now, here was A sub n. If that's A sub n, then A sub n plus 1, so I'll use a capital N since we're now referring to a specific value of n that we need to figure out, rather than a variable value of n. I know that's kind of subtle. A sub n plus 1, well shoot, I mean we already kind of wrote this down when we did the ratio test. It would be negative 1 to the n plus 1 plus 1. Okay, we don't really need that because we're going to take the absolute value. And then pi over 2 to the 2 n plus 1 minus 1 over 2 n plus 1 minus 1 factorial. Okay, and so the simplified form of that would be negative 1 to the n plus 2 times pi over 2 to the 2n plus 1 over 2n plus 1 factorial. Alright, so if we need the absolute value of the n plus 1 term to be less than 0.0005, then that implies that we need basically this, because the absolute value would squash that. We need this to be less than 0.0005. Now, good news, bad news on this one. In the past, when we've set up these inequalities to try to figure out how many terms we needed, excuse me, we were able to solve the inequality analytically. Basically, we rearranged stuff until n was by itself. That's kind of hard to do when you've got a factorial involved. But here's the nice thing about factorials. They grow super fast. Since factorials grow super fast, there's a very good chance that this fraction gets to be less than that number before n gets to be very big at all. Which means we could figure out what n is really just by guess and check. Okay? I know that doesn't seem overly sophisticated, but it's a very reasonable way to approach this problem when there's a factorial involved. So here's what that guess and check looks like. Okay, I'm going to start by, I need to move this to a place where, yeah, there we go. I'm not getting too much. Yeah, I'll put it over here. I don't want any reflection of my webcam. Alright, I'm going to press 1. Okay, 1 is the first value that n could be. And I'm going to hit enter. Now what that does is it stores 1 in my calculator as answer. Okay, I can get answer back. Answer is a blue function, so if I hit the blue key and then press this button, then it gives me back my last answer. And right now 1 is stored as my last answer. Okay, so that's what I'm gonna use for the n. And basically I'm going to type the left hand side of this n as it is, but I'm going to put in answer where n is, because I want to be able to change that part of it quickly. All right, clear that out. So I'm going to enter in pi divided by 2 to a power of 2, and instead of n, I'm going to do 2 answer plus 1. I'm going to close that power in, and now I'm going to divide by my factorial. So for my factorial, I have 2 answer plus 1. Okay, now on this calculator, to get the factorial, I need to use my probability menu. Okay, there's my probability menu, PRB. In the probability menu, factorial is right there. Alright, so I hit enter. That gives me 0.645. Alright, what that tells me is that if I did a partial sum with just the very first term of the series, I could be off from the true sum of the whole infinite series by this much. Okay, it might be less than that, but definitely no more than that. Alright, well, we want to shrink that down to 0.005. So here's what I'm going to do. I'm going to clear that. I'm going to type in 2 and hit enter. Now 2 is stored as answer. I'm going to press my up arrow key, okay, until I get back to my pi over 2 raised to the 2 answer plus 1 and blah blah blah. Now if I hit enter, it'll recalculate it with an n value of 2. Okay, aha, the fraction is dropping in size quickly. So it looks like if I do a partial sum with just the first 2 terms, I would already have an error of less than 0.079. Let's see what happens if we raise n up to 3, run the calculation again. Okay. Well, now my error is 0.0046. I need another 0 in there. We're getting there. I mean, it looks like basically we're looking up, we're basically moving everything over by a decimal place every time. Let's do 4. N is 4. Alright. Arrow up, run it again. Aha, check that out. 0.00016. That is less than 0.0005. Okay, so just kind of through a guess and check, we can say that this implies that n is greater than or equal to 4. Okay, which means, going back to my series, if I add up just the first 4 terms, okay, if I add up just the first 4 terms, that should give me an approximation of the entire sum of the series that should be accurate to 3 decimal places. Let's try that out. Clear all this out. You know what? Since I'm going to have to be using pi over 2 over and over again, I'm going to store that as my answer. Okay, just so I don't have to type pi over 2 in all 4 of these. Alright, so I want answer minus answer cubed divided by 3 factorial plus answer, remember answer is pi over 2, to the 5 divided by 5 factorial, and then finally minus answer to the 7 divided by 7 factorial, and that gives me 0.9998. So let me see if that is accurate to 3 decimal places. Well, let me see. If I rounded that to 3 decimal places, that 8 would make that 9 round up. Okay, so that would give me 1.000. Well, if that's accurate to 3 decimal places, it makes you wonder if the true answer is 1, doesn't it? Okay, it turns out that that is the case. Okay? In chapter 6, we will show that the sum of this infinite series is equal to sine of pi over 2, which equals 1. So we did in fact get an approximation that was good to 3 decimal places. All right. Now, I don't want to spend a lot of time on this, but I do just want to mention that that's actually of huge significance in a historical manner. Sine and cosine go back to ancient Greece. The Greeks invented them for studying problems in astronomy. Okay, but they didn't really have a good way for computing very accurate values of sine and cosine. They maybe knew them to 1 decimal place, but they didn't know how to get them further than that because they didn't really know about infinite series. This stuff that we're doing right now, using infinite series to compute values of sine and cosine, was worked out by Indian astronomers in the early 1400s. Okay, and it had a huge effect on the world. Okay, the ability to compute sine and cosine accurately meant that we could do astronomical calculations accurately. Okay, that completely revolutionized science, and it also revolutionized world trade because it made open water navigation possible. I mean, it was a very short time after that people were sailing across the Indian Ocean. Nobody had ever been willing to do that before. Okay, well, I'm exaggerating. That's not true. Polynesians had been doing open water navigation for thousands of years, but nobody in Europe or Asia had been willing to try it. Okay, it completely opened up the world to globalization of trade in the early 1500s. Hugely significant from a historical standpoint. All right, there's one more thing I've got to talk about. There's another little test, and I call this one a little one because it doesn't come up often, but when it comes up, it's definitely the best thing to use. Okay, this test, I wrote the wrong thing in here. I gotta fix that. I wrote that I copied and pasted, and I meant to fix this. The test we're going to talk about now is the root test, and the root test is probably not on page 509. It is on page 513. All right, so let's go to page 513 and look at the root test. Alright, so here's problem 328 in the book. Now you might notice right off the bat that rather than using n as the index of summation, this problem is using k. No significance to that at all. You can use whatever letter you want. N and k are both popular choices. Okay. Now, let me tell you what I see in this problem right away. I've got this fraction raised to a power. If the only thing that was here was this fraction, I would know that this fraction is converging on 1/2. Okay. Now, if it was just the fraction converging on 1/2, I would know by the divergence test that the series is divergent because the terms aren't going to 0. But what I have is something that's converging on 1/2 and it's raised to a power. Okay, a power of the variable that's changing from term to term. Okay, that's like the geometric series where r is 1/2, and that's a convergent series. So my guess going into this problem is that this is probably convergent. It's probably like a geometric series that would have the form of 1/2 raised to a variable power. Okay, and in fact, if I use the root test, I can show that it's convergent. Okay, here's how I use the root test. I take the limit, so it'll be k going to infinity, of the kth root, and inside that root I need to take the absolute value, okay, of the kth term. Okay, and that kth term is k minus 1 over 2k plus 3 raised to the k. Okay, now the reason for the absolute value is just because if there was like a -1 to the k, we would need to squash that. But since there's nothing like that in this problem, the absolute value can just be dropped. Okay, and if the absolute value is dropped, then the first thing that's going to happen is that our kth root is going to cancel our kth power. So we just have the limit as k goes to infinity of k minus 1 over 2k plus 3. No powers, no roots. Well, that limit is 1/2. Now, remember, the conclusions for the root test look a lot like the conclusions for the ratio test. For whatever reason, I'm having trouble displaying my... There we go. I just wasn't clicking it very well. So in particular, if that limit that we're calling rho is between 0 and 1, we can conclude that our series converges absolutely. Okay, so this series converges absolutely by the root test. There's really not very many situations where the root test is useful. It's really just for this kind of specific situation where what's inside the series, what's the formula for the nth or kth term, is something raised to an nth or kth power. But in that situation, the root test is definitely the easiest thing to apply. I wanted to also do problem 329, very similar to 328. In 329, we're given that the kth term of our series is 2k squared minus 1 over k squared plus 3. But then again, everything is raised to a k. So if you see something like that, I mean, that's definitely a signal that you should be using the root test. Now, when I look inside at this fraction, I see a fraction where, alright, the top and bottom are degree 2, so I look at the coefficients of the leading terms. This fraction is going to 2. So basically I have a geometric series where the r value is 2. So I would expect that this one is divergent. Okay, and in fact, when I apply my root test, so I'll take the limit as k goes to infinity of the kth value, or the kth root of the absolute value of 2k squared minus 1 over k squared plus 3 to a k. Again, I can just cancel my root against my power. The absolute values aren't really doing anything since nothing's negative. Okay, and so I just get, that's the limit as k goes to infinity of 2k squared minus 1 over k squared plus 3, which is 2. And again, if I look back at my root test says, hey, if you get a limit that's greater than 1, your series diverges. Okay, so by the root test, this series diverges. All right. Well, that's everything I wanted to go over for section 5.6. That caps off this section and also this chapter. So we'll be moving on to chapter 6 next week. Looking forward to that because I really enjoy actually getting to the process of building power series for functions. It's just such a powerful thing. It seems like kind of an oddball thing because at first it's like, what does this have to do with the rest of what we've been studying in calculus? But this is actually a big part of why calculus is even relevant. Calculus is relevant because we can apply it to functions that actually show up in science and engineering. Okay, but this is an important bridge between the theory of what we've been learning and actually applying that to real functions. Alright, well that's it for this section. I hope you all have been staying safe and healthy. I hope you all have been able to stay home as much as possible. If you're out there working around people, gosh, I just wish the best for you. I hope you have good equipment. Take care, wash your hands often. Um, Stuff's pretty serious. I'm not trying to lecture you about it. I'm just genuinely concerned about people. Take care, my friends. Bye.